Hi everyone, my name is Daniel Moyer, and today I'll be talking to you about the content of a paper from MICCAI 2021 from our group. This is work with Polina Goland, who's a PI in MIT CSAIL, but also our collaborators at Children's Hospital at Boston Children's. So that's Ellen Grant and William Wells um, and Ezra Turk. Yep. So today we'll be talking about efficient tracking in 3D imaging. And when we're talking about tracking, we're thinking entirely about rigid motion. So this is a MRI of a brain, and we're thinking about motion that can be described as a rotation matrix and a translation parameter. So a movement in 3D. And we want to do tracking, so we want to estimate these parameters from two pairs of images. Maybe a reference image and then a current image of where the brain is at currently. Right. And so this is a special case of rigid registration. So if you had two objects in general and you wanted to register them to estimate these parameters, this special case knows that it really is truly a rigid motion. And in this case, we want to go as fast as possible. So of course, we want to do this on the GPU using a fixed fixed amount of computation, so no iterative optimization. Yeah, and we would like to use this inside of other methods, so compose this method either before or after. And for methodologists, this really means that we need the entire method to be differentiable. So great, we're trying to do rigid motion, and our application is actually some type of real-time MR system. So we're not all the way there yet, but we would like to apply this in fetal MRI. So as you can see, there's a lot more going on than healthy adult human brains. In fetal MRI, we have all kinds of things, and we really want to track just one object, the fetal brain. But you also can't tell them to sit still, so we have to do tracking. And the way we're going to do this, or at least the way that we've chosen to do this in this paper, is to use equivariant convolutional filters. So a regular convolution is shown in the center, and as it rotates, you can see that the convolution orientation, the positive and negative, so the red and blue, stays oriented in the same direction, left to right in this case. Even though the brain rotates. So we feel like the red and blue should rotate with the brain, but actually a regular convolution doesn't shift with it. It always stays oriented in the same way with respect to the frame. On the other hand, an equivariant convolution, shown on the right, is always oriented in the same direction as the brain as it rotates and translates. So this is anterior to posterior. The red to blue is always in the same relative orientation with the subject, and not the same orientation as the image frame. Yeah, so we're using the convolutions on the right-hand side. If we're able to construct a convolution such as this, we get this sort of more technical description that the filters, the features that we've learned, the convolutional filters, they commute with the translation and rotation operator, the T operator. So if we have an image and it's truly the translation and rotation of another image B, maybe below, then by applying these filters to the other, to both images, we know that the filters of the second image are actually a translation or rotation of the filters of the first. And we can construct these from a basis of all filters that that obey this property. So this is most recently expressed in Maurice Weiler's paper in 2018, but there are hints and flavors of this throughout computer vision since steerable filters in the 90s, and from long before in physics preceding that. So again, yeah, we now know that if we apply these filters to two images, which are secretly a translation or rotation of each other, that the filters themselves will be a translation and rotation of each other. Great. So that means that summary statistics will also be a translation or rotation of each other. So maybe the spatial mean of each filter, or the weighted spatial mean. And if we have an array of points, or a set of points, and a second set of points, which we have corresponding to the first one, so the first point corresponds with the first point of the second set, and so forth, then we know how to solve the best transformation between them, or the best rigid transformation between them. We can do this using SVD, and we've known this since the 80s or 70s, actually, that this is a weighted least squares problem. Great. So before we move on, all of the learning takes place on the left-hand side in the screen box. So this entire network is the convolutional filters that we're learning, the equivariant ones. Afterward, aligning the point clouds is completely closed form. And this allows us to essentially encode all of the symmetries of physical motion and all of our pretty good knowledge of that into our network without having to relearn it at the convolutional filter level. So this tends to outperform regular convolution. These are two baselines. And in our fetal data set, this works even better because the fetal brains are, well, highly variable and smaller. So this is actually a much harder task. And yes, so you can actually train this with only one data point. So the training set is the two poses on the left-hand side. Again, these are in 3D, so they're about a million voxels, right? 128 by 128 by another 128. So we're only seeing 3 slices of them. Yeah, so if you only train with these 2 poses and you don't do any augmentation, you can still achieve pretty good accuracy. And yeah, so traditional methods use iterative optimization, which might be a little slower, but if you have the time to do it, this doesn't really replace it. It's more that we could use these levers together, and that these new levers that we've introduced are completely orthogonal to the previous methods, that it's something radically different. So if we're designing a system that requires rigid tracking, this might be one way to do it that is unlike the others. It's also fully differentiable, so you could put this inside of other training schemes. Yeah. Thank you for listening. Our paper is on the internet and also available at the MICCAI conference this year. And our code is also on the internet. Please feel free to reach out with questions, and thank you for listening.